All right, we're ready for the final installment of compact quantum surfaces. Elmar, it's all yours. Take it away.
Instead of summarizing what I did last time, I finished what I didn't finish. That was a classification. Let's see if I get used to it. Classification of the non-orientable. Orientable quantum surface. I'm paper for the discussion. What I did, what I tried to explain with my assigned of an arts was I forcefully wanted to have the classical counterpart, but that's completely unnecessary. Like if I get isomorphic algebras, why should I distinguish between something which is classical or not? So now, to define my non-orientable quantum surface, let me take A1, yeah, you know already, arcs. So up K, each arc like a double, and then we started taking arc. And the one with another one with inverse orientation. So this is an arc in different orientation up to this plus one, thanks. Plus one up to n, an minus one. So the parameters, these arcs as a unit interval goes to the boundary of the disk, do this, close, do this, such that, and that's the only thing which I need to require, that's a quotient. So we take the boundary, well, yeah, that's the only thing. So on the boundary, I can fix the quotient, that this will be isomorphic to the wedge sum of n circles. So this little requirement, it mainly says that each arc starts and ends at the same point. So you know, you remember that this well, okay, here it's HAD is equivalent BJD AGD equivalent to AG minus 1T. This is for J bigger than K, and this is for J up to K. So, and then we define our quantum surface C, B. So I keep this parameters because they will not be isomorphic as doublets operators such that, so these are doublets operators such that applying the symbol map, I can say, since what I can write it here is an element in the star algebra of P mod our relations. So to classify them, I started what I discussed last time was, so I'm interested in isomorphism classes. I observed that the compacts are inside, then each isomorphism is given by a unitary operator on Hilbert space, which tells us that isomorphic C-star algebras are strongly equivalent in the sense of the theory of extensions. Extensions we can turn in a group. These extensions are usually these are groups. You take extensions which are strongly equivalent, not the trivial extensions. So, and these groups, in our nice case, are classified by K homology, and you want to do the same thing now. So, to show you that which ones are isomorphic. So, we take a compact set, so that we can, well, let's take one morphism from the boundary, Gaussian map to which are the arcs, and then some isomorphism, homomorphism to a compact set in the complex numbers, which we define as the union of circles J from 1 to n, J plus 1 J. So these are is a radius, and we shift the center by 1 over J. So they have all these circles have 1 as a common base point. Then we take the identity function on Cx and Xn, or the identity function. And this function certainly separates the points of Xn. And if this is a homeomorphism, it certainly separates the points of our Gaussian map. So it generates these functions on the wedge sum of circles, and therefore we get a generator if you pull it back to a Toeplitz operator. So to pull it back, or it depends on n.
Sorry, Elmar, I cannot decipher what you wrote. Z of what?
Z of x plus y.
Identity.
Let's see.
I y.
So plus is that plus I think beyond I.
Okay, thank you.
Complex number.
Yeah.
Yeah, I don't like the correct name would be the identity function, but I have feeling the identity function is strange. So I prefer Z. Now we pull it back. So we pull back. So Z we define as a pullback. Phi n pullback of Z. So this is a function on the circle that satisfies exactly the boundary conditions. And since this is a homomorphism, separates the points that it has to separate. Now we need our Toeplitz operator where defined by functions on the closed disk. So we define continuous functions on the closed disk by just multiplying with the radius. So I, this should be theta. So we multiply by I, and here we have the functions on the circle. Maybe I should really denote it by n. So okay. And that gives us a generator. So then our quantum surface P and K. So this operator is an element of this style sheet, generated by this essentially normal operator. One Toeplitz operator. So if I take the Toeplitz operator, if I take the symbol map, it's a restriction on the boundary that separates the points. I can take it the edge point or leave it, and all the compacts. And this gives me an C star extension with between, so we have C star extension, compacts, quantum surface, a Q, and then over CXN is compact set in the complex numbers.
Could you explain why this is, why one and this T is the generator?
This element, if I take the boundary map, it separates the points on the quotient of the circle. So we defined it. Our first we define all doublets operator that satisfies this boundary condition. Now this is a commutative style cheaper. Stone-Weierstrass tells me if I find one generator that separates the points, its polynomial algebra, the closure of the polynomial algebra generates the whole C-star algebra. So any function C I can approximate by polynomials in D. Well, I actually, because of Stone-Weierstrass, I always prefer to include its adjoint. And I take the compacts. All the compacts.
What do you mean it separates the points? Like what's
It's 2 points. So it's this function. So if I have P and Q in my boundary circle, but not my equivalence relation. So my function psi, which is actually it's the symbol mod of my generator. So P will be different. So if you take different points,
okay?
this psi has different values. It takes the value in xn, but it has different values.
Okay.
Maybe a quick comment. Here we have only one function, so this separation of points boils down to injectivity, but still in general you can speak about separating points with respect to some family of functions,
Yeah.
and then the condition turns out to be that there is some function in this family for two distinct points P and Q. There is some function called f in this family such that f is.
That's what I was thinking. Yes, but
You have only one
function that does this.
actually, that's why I use the identity. So I put it, if you look at xn, I think the identity always will separate points.
Yes, but I think that the confusion may arise from the fact that if you have one function, this is just injectivity, but still you can speak about separating points with respect to some family, and then it is called like that.
But for me, it's important that I have one generator because the bound-back Spilmer theory classifies normal operators with essential spectrum, in this case xn, that are unitary isomorphic up to compacts.
So normal, essentially normal.
Essentially normal, with essential spectrum xn up to compacts. And this I will use to show which these diagonals can be isomorphic, will be isomorphic. Okay, I have to thinking. Maybe. So now we have the generator, and then I give another generator. So, well, the theorem will be C. So our quantum surface, I give another generator, which is very concrete. Is isomorphic to C star algebra generated by one essentially normal operator with the same essential spectrum. So T, let's take NK. I included adjoints and all combines. Where now I give this operator, I can give a very concrete description. We did it last time with unitary bilateral shift. Now P is a combination of unilateral shift and bilateral shift. P is orthogonal sum. So you want to have spectrum xn as a spectrum. So I take j plus 1 j. This is a shift minus shift spectrum. So in that s squared j equals 1 to k. So this is one operator, so one set of operators, and then the rest will be again the bilateral shift, the unitary operator. So k plus 1 and j plus 1 j. See, this is just we shift a little bit the spectrum, so this operator separates the points. It has essential spectrum xn. And the proof.
So this phi alpha depends on this A and B. This phi of alpha, this
There's a phi, yeah, I know, there was, yes, this one.
yeah, depends on.
Yes, actually, I use a phi for ordering. Someone can, it's another person takes marks, so it can order it a completely different way. So I will use this phi to order, I can make a permutation and flip the orientation. This is lovely. It's a difference. So PDF theory would make a difference if I take here the adjoint S star squared. Now, since I take the adjoint, my systology was isomorphic, but they define different elements in the group of systology extensions. So the phi is very important that I can order the first ones. I order the first ones that have appear double, and the last ones appear with its inverse orientation. So the proof is.
Sorry, in the previous example, in the previous lecture, you didn't have this BK, and then.
He had it.
But not for this identification of a different generator, yes?
What?
The different generator, we were only discussing this orientable case.
Yeah.
And then we only had U.
Exactly. We only see. Now so I call something non-orientable if k is at least 1. I need one pair, and that's
responsible for the first part, for the first case sample, which are unilateral shifts. Yes. Yes.
Yeah. Exactly. On. So yeah, shift operators on, of course. Sum j from 1 to k L2, and the other ones are the shifts. K from k plus 1
this other
and
one of the generator. This was not discussed.
No, that's last time it only the oriental case, and check with the remark observed immediately. These were all trivial extensions.
Yes, there were some remarks about the non-orientable case, but we haven't discussed these generators.
Yeah, this one we had is a problem was I completely unnecessarily I was explaining Z should be the quotient should be really So classical equivalent should be a compact non-orientable surface. That's absolutely unnecessary because these star shapers are isomorphic. So I don't have to care about it. Now, any arrangement will be fine. Now, if someone has some permutation, my phi end is corrected. Any permutation is allowed. Orientations, I make all the orientations well, is a positive or negative. So here I make positive orientations to get S squared. So if I define the same operator with that joint, it's the same star cheaper. Okay, and then so proof would be the proof is nice if you like this PDF theory. So there is a theory of extensions. So we are looking for extensions of CXN over the compacts. Usually one doesn't write it. So I have to show now as equivalence relations is strongly unitary equivalence. That's what also I'm discussing here. Because of this isomorphism between the compacts, there will be a unitary that turns one generator and the other mod compacts. So this group is known, well, Kasparov rated it up to the KK theory. Now the compacts are stabilization of C. This we know as K homology. And we know our K theory. This is the number of cycles. Any cycle has a generator, so it's finite. It's free, so it's isomorphic to K theory. That's just with N.
So, and how do you know it's free?
These are just cycles. Where is it? We have a wedge sum of cycles. So you can view it. This is the wedge sum of cycles. You can view it as you take open intervals and quantify with 1 point. So each then you can take the circles. It's a direct sum of circles, and K theory respects direct sums. So if you have some.
So this gluing at 1 point doesn't bother.
I would, okay, I can write it and raise it. Yeah, K1 of the wedge sums of circles.
But now we write K theory.
Yeah.
Okay.
Wedge sums of circles. So this is I can take K theory of open intervals. And compactify in 1 point. Now, K theory of the cycle with unit or without unit is the same thing. So I can write it like K1 the sum of C0. And K theory affects the sum of.
Yeah, I've got you. Yeah, thank you so much. Yes.
It's nice that I had a chance. Now we know exactly the generates. Now we know what we mean with these ZNs. So it's good that I didn't want to write it because of the time.
So from X sub N, not for X sub N comma K.
Excuse me?
So you're looking at X of C of X.
This one?
No, right above.
Yeah.
X.
Yeah, that's
N.
Anything.
Isomorphic.
But so you're not doing the case of the theorem where you have N comma K instead of just N.
Oh, no.
So-
Yeah, the notation is bad again.
No, because the K will give you some.
Exactly. Now that's the proof. You're right. I didn't want to. Yeah, but wanted to save some notation, but that's exactly what's happening. We have to remember our K. But, well, yeah. Okay, here it is. Well, here I don't need the K. I don't need the K here because that's just types. Doesn't matter. Here it's important. It's the operator that matters, not the space are always the same. For all cases, the same space. That's okay. But now, so these extensions are generated by essentially non-operator. So I take the class. I take the generator as a class. In the style papers, our generator was the theta. And how does it work? You take the simple map, then you have the continuous function on a circle. And what we do is the k-homology, well, that's the index of points in the complement, which classifies it. We know that it's k0, so where does it go? So these operators have index 2 or -2 actually. This is 0. This element goes to -2. And now comes k. -2. And here we have 0. So we go along the winding number, here we go back and forth, and here we go twice. So this is the element in Zn. Now, whatever generator has a central spectrum Xn and has these T-theory class, they are isomorphic up to compacts. So they are unitary equivalent up to compacts. So now we know that these style cheapers are isomorphic. And we know that CP, so they are isomorphic, that's proves the theory. And we know that if I have two of this, so it's isomorphic to C. Let me try to write it with prime. So they have to define the same class in K theory, and that happens if and only if n is n prime and k is equal to k prime. So they are really different if I take different numbers of arcs that repeat itself twice. So classically, we can have if these are this arrangement will give a closed non-orientable surface. They are all like homeomorphic, but here we have a whole class. We have different random surfaces. And I really don't need to care if this one gives a random surface, because here I have isomorphic C-style cheapers. At least one version exists that gives a topological manifold.
Okay, so you identified this K1, K theory using abstract properties.
Yeah.
Computed it.
Yes, actually, it's a universal coefficient theory. Because we have no torsion and we have finite K2. So this is this is UTD.
Allow you to identify with K1.
Yeah, this is UTD. You're right.
I think also, in the Brown-Douglas-Fillmore theory, didn't they, as a special case, they worked with the compact subsets of the plane. And as you said, they completely identified by the index. And
Yeah.
so in fact, this is a more general argument than you need for this particular example.
I just switched from K homology to K theory because it's easier, it's known, and it's a bit easier. It's since I have this arrangement of circles, one goes into the other. So So it's the index, I choose the point, it's the index. But if I go twice, this one has index 4. And this I wanted to avoid, so I sum up indices. If I take this, if I would take my EXT like this, then it's the same. Yeah, this index, if I go twice, so operator, which would have index 2 here, index 2 here. But if I once in the other, then things shift a little bit. I would have to take the differences of the indices and looks more complicated.
So is this just basically a covering of S1 is Xn? It's a
Excuse me?
Is Xn
Yeah.
a covering of S1?
No, it's like this is the batch product of circles, homeomorphic. It's a written as a homomorphic set, as compact set in the complex plane.
but it's a few circles, right? Then you have
No, there's no covering. We have a quotient.
yeah. But
There's this problem point where they all touch.
Yeah,
Oh, it's a subset, not a quotient set.
it's not a covering. You have one point always appears on. You have base points. Yeah, you have two. So
Not a local homomorphism.
local.
It's not a letter projection from the universal covering.
It's not a good. Elmar, I think I'm missing n, so it should be xn.
Yeah.
A1 of xn.
Got it.
I'm sure you're right.
Height of this is simplicity.
But where?
Yes.
Thank you.
Okay, now you have to share your salary with me.
Yeah, and it looks almost equal.
Yeah, it looks like alpha.
Okay, I go to.
But Elmar, wait. So why did you bother with K homology at all?
No, the K homology.
I was completely convinced by your argument about K theory.
No, the K homology is really you have a set. And then what Jack says, so it's classified by the index. So
Okay, I got it because C of xn is on the first leg of K.
yeah, it's
Okay.
much cleaner.
Okay.
Much cleaner argument. We classify it by the index. So if I want to know if these operators are the same, I would choose a point in the complex plane in the bound complement, and then I would have to check what is the index of this operator. I say, this operator, what is the index? I compute all the indices, and then I compare the indices. And if all the indices are the same, I know they are unity equivalent up to
But
complement.
now we are speaking generators, but for K group, you don't need it.
No, yeah, well, that's a trick. I see. I see. It's so to write this. We have -2, I would have here to take the differences from 1 to the other. So it doesn't, here in this way, the index adds up. So you get the first one is 2, -4. So I would have to take differences. I didn't want to do this.
Okay, and could you explain one more time, how do you get these -2s and what?
That's the index of
Square.
S squared.
But have we proven already that it's isomorphic?
No, that's a theory. So I haven't. Should I?
I'm confused in the logic. I mean,
Yeah, let's take another slide. So we have xn was something like point circles. Okay. So we had something like this vector of circles. Okay. Now, so let's call. I would like to take a point. No. Okay. So let's see if I can. So I take points here. T1. T2, it's just a point. Here it's a small t3, t4. So the essential spectrum, so
But these are points on circles,
no,
No, in
they are in the
area bounded.
in the bounded complement of the spectrum.
Okay,
So
okay.
the spectrum, essential spectrum of this operator. Now, operator now, yeah. We take the operator, let's any, so, oh. So the operator, which I was calling something like NK, is N. Now, two operators. So an operator T in essentially normal in pH essentially normal. This essential spectrum, so I take spectrum, sigma T is a calculus algebra, Xn. So these are candidates. So if the essential spectrum is different, no way that it can be unitary equivalent. Is unitary equivalent to the other?
Essentially. Good.
Mod K, unitary equivalent to our generator. Generator, which I defined for all these. Well, I've defined this operator, and then I said, all the other generators are unitary equivalent. Mod K. That means essentially unitary equivalent. Mod the compass. So if and only if, and now since I have these holes, I have numbered if indexed. So none of this point is in the essential spectrum. So they are invertible in the Calvin algebra. They are Fredholm operators. It's the index, the Fredholm index of T minus pi I is the same as the index, and now is my generator, which I explicitly define. T N K minus I. For all I.
This is Brown Douglas field.
That's on Douglas field. That's the first version, let me say that.
Difficult here.
Yeah, that's the first version of Brown Douglas field. That was a big success because it related the question when are essentially normal operators unitarily equivalent mod K to something in algebraic topology. The algebraic topology of this set determines when operators can be essentially unitary equivalent. So essentially normal operators can be essentially unitary equivalent. It's a set. That's really bounded. That's similar.
Special case of this theorem, is it true that if all those indices are zero, then and the operator is it's essentially unitary equivalent to some compact perturbation of
Normal
unitary
operator.
normal.
Exactly.
It's true, yes.
That's true. Yeah, and that's true because this corresponds to the trivial extension, which means you can lift your essentially normal operator, you can lift to a normal operator.
Yes, but still it is true for any possible choice of essential spectrum, yes?
Yeah.
Very easy to prove is just work out this case of essential itself adjoint operator. Then the situation is very easy. You don't need the
Neumann-Weil. That's Neumann-Weil theory, and they are all diagonalized. But here it's really and This is the advantage of talking about groups. These are, if the indices are zero, this is a trivial representation. So this is a trivial extension, and trivial extension, there's a Busby invariant, which I didn't mention. The Busby invariant factorizes for as a homomorphism in the bounded operator. So if you get a homomorphism, its image of the Busby invariant is a normal operator with the same accidental spectrum. That's even the way you would find it, but it's not constructed. But it exists.
Like existence of a lifting, yes?
Yeah, there exists a lifting, which is also homomorphism. And since this is a homomorphism, it commutes. This operator is commutes with its adjoint. You find the lifting of this commutative histology power over the spectrum. You find the lifting in the bounded operators, and the generator commutes with its adjoint. That's true. It's nice. That makes theory really nice. It's a long way. Well, Kasparov really started to observe that you have two histology pairs. You can define the invariant functor. But if the histology pairs are not so nice, then problem starts. So the first problem is how to define the addition. Well, then we have compacts, you have stabilized. So compacts is you can double the Hilbert space, and then you get again a copy of the compacts. That's it.
But I think that the addition is not the problem.
No.
The other element is problem.
If the inverse element is a problem, and then you need generalized. Excuse me?
The neutral element is problem.
No, that's not the trivial ones. So not the trivial representation. These that live to homomorphism are considered the trivial extensions.
I think that all trivial extensions are unitarily equivalent mod compacts. That was a key part of the paper. That's exactly what you were, Adam's referring to.
The problem is finding an inverse, and then that's generalized Steinstein's theory. So these homomorphisms in Kalkin algebra, the Busby invariant gives you a homomorphism in the Kalkin algebra. Now, this well, an homomorphism is a completely positive map, and then you can lift it to a 2 times 2 morphism of the bounded operators, and the corners. Well, there's this corners. One of the corner is a Busby invariant, and the other is a Busby invariant of the inverse. That's where the problem starts. And then it gets more and more complicated. So to define this as a group.
Wait a second. So now what you wrote makes sense because PI is a complex number.
Yeah.
Okay, so this is what you were saying, that it's easier when you have everything.
Yeah.
I mean, but yeah, I mean, it's a commutative system algebra, but it's just a bunch of circles. So we think about
I think it doesn't reduce to just index data.
Yeah.
It's higher than 2.
You see, if I take.
Yeah, exactly. Yeah. Okay.
If I take here's the orientation, what I didn't want to avoid is, so the index of B1 would be 8, and then the next would be 6, 4, 2. And this I didn't want to avoid. That's why I jumped to K-theory.
So you argue in this way by BDF that in fact we have this isomorphism of sister algebras.
Yeah.
Because this T and B of H, that's exactly what you have in your system.
But I argue the other way around. If I have an isomorphism, I have an isomorphism of the compact operators. That's always I can implement it by a unitary operator. So any isomorphism of these histology pairs is implemented by a unitary operator on the bounded operators.
What confuses me is that you are doing two things at the same time. One thing for me is this if and only if classification of all these sister algebras, and another one is isomorphism to being presented by
there is something which is not quite correct, because the Brown-Douglas Filmer theorem classifies essentially normal operators, not histology. So the first observation from the last lecture was I can implement an isomorphism by using a unitary operator.
Okay.
So I can reformulate my problem in histology extensions that are strongly unitary equivalent. Now, there is this, we talked about it quite a time by this phi. So this phi allows me changing orientations and the order. So, for example, the extension, if I take T equal to shift, and then D equal to S star. So these operators both generate the doublets operator, but
Wait,
C
it's
define
the same T.
D star. Well, T prime.
Oh, yeah.
Okay, yeah. So these operators
Mhm.
generate the same star algebra. So
Yes.
that's this algebra.
Yes.
But they define different extensions because this has index -1, this is index 1. Yeah, different extensions. So in
Yes.
the classification of
Yes.
contact with Fillmore, these are different. Next,
Yeah.
these are inverse. Now, if I take F plus S star, so I'm missing something. So I add some compact, and then I get divided as a little just on to Z. And that's the way. So I sum these and get something trivial. So the extension with this normal operator has an inverse given by its adjoint.
Okay, fine. Can you go back to the previous slide, please? Okay, so here we have two statements. One is this implication, and one is this isomorphism, right? But it's really whether C, P, N, K, Q is isomorphic to C server generated, blah, blah, blah.
Yeah, exactly.
So what do you argue first?
First, okay.
Because for me, these are two independent statements.
Yeah, it's really has to be made clear. So I define it as these operators. And then I say, now in C star algebra, I find an operator in my C star algebra, which generates my C star algebra and is unitary equivalent to this operator mod convex. So maybe the first step is, let me say, the first step is I define an operator.
Yeah, that's fine.
And then I say, this is star algebra. I can find in this star algebra, I find one generator which is unitary equivalent to this mod convex.
You could add this column. T.
Excuse me?
Column. You can add a column for equality.
Here. Yeah, that's right. Sorry. That's the first thing is I have a guess. So I define this operator.
Okay, but how does it imply that you already have isomorphism of sister algebras?
Now the whatever I
see that one is a sister subalgebra in that. That's okay, but why is it the same?
Why it's the same? So I think I have
Index.
I find an operator.
Okay.
C and U star. It's equal. Gives me a T and K plus some compact perturbation. Since I have the compact inside, I can subtract this compact and this and these.
Yeah, because you know that this T whatever head is a generator.
Yeah.
Okay, that's what I want.
Yeah.
Okay, so now I understand now why you claim that this is an isomorphic sister algebras. And now how do you get this implication that
anything? So I think so. Any sister algebra has some generator which fulfills this. So if I have another one, then I get a B, that is better B star is B and K, so this is B plus some K prime. Now, so from there, I get that So the E star U the theta hat U star E. This is D psi hat plus some other complex. Twice.
Okay, but please correct me if I'm wrong. So the index computation allows you to conclude this implication.
Yeah.
Okay,
Unitary equivalent. This is the existence of this unitary operator in PH.
whereas the first statement, it's just because you have this unitary equivalence modulo compact
Yeah.
to this generator.
Yeah.
Okay, I'm happy.
Oh, great.
Sorry for the interruption.
No, I'm used, and I don't know if I can make it to my.
You still have 1 hour and 9
Yeah,
minutes.
spectral sequence is a complicated thing. So I don't know if but you see obviously that we can write, okay, we want to have it as a CW complex. I try.
Before CW complexes, could you compare this classification with the classical classification of non-orientable surfaces?
Naja, we have more isomorphism classes. So in the classical case, it doesn't matter how many circles appear twice. At least one has appeared twice, and then you have the other ones. The other ones are A inverse, so you can cut and glue until you get
Yes,
a normal form.
asking what is happening if you take a classical analog of this construction. I'm talking about the classical classification of non-orientable surfaces.
Yeah,
So these elements, this
yeah,
earrings, okay? So they define, for instance, some elements in first homology group or in the fundamental group.
yeah.
So how to relate this classification depends on the very complete realization
No.
with the classification of classical surfaces plus some additional topological data.
No, in the classical case, you cut on base until you have some normal form. You can always find a homomorphic assignment, which is normal form A, B, A1, B1, A2, B2. You can always get a normal form. So you can arrange it, you can order it in the classical case.
Yeah, my question is how this pair Kn could be compared with classical invariants of non-orientable surfaces.
Yeah, I don't know.
The pair Kn,
There is nothing else than they are all so these.
for instance, in the non-commutative case, you
Have something like this. No?
you cannot regard these circles as generators of neither fundamental group nor generators of homology. You can relate the number of them to some index computation.
No, always this happens. They're homomorphic.
Mhm. Yeah.
So any topological invariant.
But you're talking about the classification of isomorphism class of some construction.
Well, but this cannot be topological invariant.
I'm asking, yes, so I know, because I said that
Yeah.
cannot be interpreted in a commutative situation as something of topological
Exactly.
meaning. Okay, but classically it can.
But there's not a.
These A1s, inverses, okay, formal inverses, they generate some generators of the fundamental group.
But it's always the same fundamental group.
Yeah, but that's not what he's asking. He's asking, is it possible that outside of this construction, you have some other classical non-orientable surfaces which are not covered by this construction?
Well, if you don't care about.
My question is, what do you classify? Some construct-
I classify in the non-commutative Sitalchipas.
Which are got from that is, so from
Yeah.
some construction.
Yeah,
So you are classifying isomorphism class of some constructions.
Yes.
yeah.
Okay.
And so, but the problem is really, I can assign arcs which do not give a classical two-dimensional closed manifold. I can construct something like a sphere and then identifying 2 points. So yeah, okay, CW complexes. Okay, obviously our wedge sum. You can use this one as a one skeleton. So we have intervals and a point, base point. And circles. And our construction then, so we can, our C-style keeper, we can write as a so here we have at a map, I think it was something like phi. Well, no, we take, okay, let's take C1, CS1.
And why do you call it X1?
Like
Because first step in your.
it's a
Okay.
one skeleton.
Okay.
So like we can take here the pullback of the quotient map. While this one is isomorphic to doublets over the compacts. So here we have the simple map and the doublets we identify, well, that's the wrong way. So we identified with a non-commutative two-disk, closed two-disk. And if you look at this pullback, so this would be my X2, which is doublets with a one skeleton. Here we had the quotient map, and this is our row star. And what if you look at this, what does it mean? So we have a doublets operator. That the doublets operator, its symbol map comes from a row star, which means the doublets operator should satisfy the boundary condition. It's really our surface can be constructed in this way.
So what
That we can, that's already non-commutative.
row is what the embedding?
So we have rho was the boundary to its quotient.
It's like a restriction, row-like restriction to the boundary.
So that, and then, okay, we should combine it with some isomorphism. Say that's a wedge sum of circles. Then I put it back. So. Okay, and then I don't think I get my, instead to my, I will get to my spectral sequences. So we have already two non-commutative CW complex of 2 dimensions. What I care is, so that C style shape as given C B, let's this, I keep this of dimension K, non-commutative. The C style shape so for each K. With an ideal, closed ideal. C0, just notation, but it is the algebra. K in C, right, K is right. That. Yeah, so we have C0, K, Q, C, P, Q, K, and the quotient. It's quotient.
So what you have tensor powers of Toeplitz.
No, yeah, that's an example. That's our example. But I just say, I don't care what it is. What I want is. So it takes a quotient, which we denote then by the star algebra on the boundary. CD. Have the same case theory as classical analog. That's the only thing I care.
But that's like our definition, right?
Exactly, but you take correspondence and I take C-star pullbacks. You are even more general. Same case theory as the classical startup.
I know, but it's very similar.
What do you mean by have the same case theory?
Same K groups. Same K groups.
And you don't care about what is induced by the boundary morphism.
You are not interested in short exact sequences.
Naja, well, meaning that let's just say groups is this is always trivial. And then you get only, then you have the boundary morphism automatically gives you an isomorphism. You have always, in the 6-term exact sequence, you have always trivial in the center. So the count, that is enough to say what the boundary morphism is, it's
To say
immediately.
it's trivial, do you assume that you have some
K-
generators?
K0. Of my closed disk is one from the, well, it's C1, okay. Trivial, theta 1, and K1 is 0. Of C, P, K is 0. So these are the middle terms, and then you have isomorphism on the boundary terms.
This is some C-star also, right? It's
Maybe I should really have given my examples over here, but that was.
It's unital.
Okay, let's take let's take.
So you mean quantum, yes?
Yeah.
But Q can be equal to 1.
Yeah. Got you, it's right, I should.
Q just means quantum, it's just not.
Okay, we take an example, so we don't need our too much. And that's exactly, okay, 2K. No, this, yeah, that's even, so I take doublets. K times. And the what is balls I take a closed interval. Doublets. Three times. and zero. You okay as compacts. Let me try it like tensor product matter. And here C zero. Okay,
So with all the bar.
yeah, I've seen it here. That's secure. Is zero. And then the boundary is here as a portion. So now you have disk, the inside of the disk, and you have functions on the boundaries. And then, so
These are just examples. You could take Szymański balls.
exactly. So given,
Then we should not call it like C of something Q, because it means some fixed system algebra, it's not.
no, you can even change in each K, you can change your definitions. You can take triplets, and you can Szymański-Holmes balls.
Exactly.
In
That
each,
makes sense.
I absolutely freedom. So
I mean, he's consistent. It's just notation. He has a family of sister algebras with some K theoretical properties.
Yes, that's, yes,
so here comes the
it's all not.
something.
But writing DQ to the power
It's
K.
confusing. I mean, this is why I said,
This is confusing.
this is why I said, oh, this is just tensor power these operators.
Again, you
Yeah.
don't like my notations.
So we don't.
Not me.
You have
So we
some people say a manifold of dimension n.
Yeah, that's a fixed manifold, I mean, right, the N is a.
Yeah, no, the n means the dimension of the manifold.
Mhm.
So the k means dimension of my ball.
It's like, for example, non-real Torah, like a C infinity, T theta M, is then it's something fixed.
But that-
Right, it's-
But I have a suggestion. I know that this is what we use for our employers, but instead of D, if you use B for a ball. so any quantum-
I know.
Because D is so strongly attached to this, is that when I see D to the power K, I see not the dimension, I see the Cartesian power.
When you think a tensor product of algebra, aren't you getting more like K-dimensional torus?
No, ball.
Oh, ball.
It's a ball. It's a ball.
Yeah.
Of course, you don't get circles.
No.
Because you're doing the.
Yeah.
Yeah, so, the reason why, since I had the first example with the D, I didn't want to change the almost D, didn't want to change the notation.
But it's confusing.
Yeah, what's wrong? Yeah, notation I have to learn.
We just.
I have to think more. Now, oops, we are still. So the only thing I care now is homomorphism. So you have already constructed something, you had it for K2, it's classical. K minus 1 goes in some sum of in K, some numbers of our boundary. B, should I start with B? Let's see, let's go with P now. So, is the star homomorphism?
And Q.
Yeah, thanks. So then we define one higher. C, X, P, Q. So as a bullback. It's the ball. Closed. Yeah, I'm with the T again. Plus our X K minus 1, 2. over 2 math. Here just sigma, I keep the sigma, I like the projection quotient map, and here that's my fluent map, which will decide what we are constructing. So here it goes to the balls, say from NK. Yeah, it's a projection in my CX A minus 1 cube. We had our tau K. So here I can really write it's a quotient. E K by C0 Q Q 0 P Q. Okay. And here it's a quotient math. Okay. So this is always projected, and then you know this is projected. So I wanted to go to spectral sequence. Maybe I just jump to it. Because you know we have seen a lot of these constructions. Nice construction is projective space. I could make it if I have time. Now, where comes this spectral sequences in? So remember, this is just the projections on the right. Here we have projections on the left. No, that's not good. Let me call them. Okay, just to try it a little bit less. So remember this one. Okay, I go to another page.
Another page of a spectral sequence.
Excuse me?
Another page of a spectral sequence.
It's first page. Your page.
So denoted this southwest arrow
Yeah,
like a projection.
this is a projection. It's really a projection.
It's not a projection.
Nah, it's a projection. It's taking the second from the full back.
It's induced by projection, but
Yeah.
could be not subjective.
Yeah. No, that's subjective because we had this other arrow. Yeah.
No.
Okay,
Southwest.
let's go.
Let's go back. Go back.
What's the
Southwest. This one.
This one?
No. Southwest.
Southwest is.
This one. Okay. Southwest.
Yeah.
Southwest.
Okay. West.
Southwest.
Here, this
Left
one.
upper. Left.
Yeah.
Not a projection.
Right. Well, that would be, yeah, okay. Yeah, you're right.
But why does this? Because you take it upside down. Okay.
Yeah, well, that's, I can say it's restricted to XQ, okay? So that you know, this is the map which I wanted that you keep in mind.
It is also restricted, but this restriction is subjective.
Yeah, you're right, I know. Southwest, I will. I lived in the east alone. 6. Okay, so the map, I changed this map to row. So what we have is X, Q, N, O, N, and subjective because the other, the parallel map was a projection, was always subjective. And it should be, it just means that we can, the n-1 skeleton, we can, it's a closed subset of the n skeleton. And then we go on and on and on. To C X. I put the Q. more likely to be commutative. Row 1, C0 just points, leaves the Q, and row 0 goes to 0. All these maps are surjective. And this gives us a filtration of ideals. So I start with A minus 1, 0. I don't know if it can be seen. So minus 1, then A 0 defined as a kernel of O n. Then it goes A1. O n minus 1 O n. A should be the kernel of O n minus k up to O n. So then goes on. A n minus 1 is the kernel up to O1. And finally, AN is the kernel putting the zero homomorphism, that's the total space. X, U, N. So the filtration of ideals is, yes, A minus 1, A0, A1, up to A n minus 1, A n, which is total space. And to a filtration of the ideals perfect, defines a spectral sequence which allows to compute the K-theory of the created object. So there will be an extension problem. But it is so why does it is so I consider it useful, and I hope that to really be able to compare to the classical way, to the classical case. My cluing map tells me how should I clue the boundaries of the disk to the x k minus 1 skeleton. So if I know the K-theory of the skeleton, I know the generators, so I can identify the generators. And I can say if these maps are the same as classical, then hopefully can prove that we don't change the K-theory. So why are the spectral sequences so powerful? So these A's, let's write it, which is so what is A0? Let me write A0 as C0 XQ. So we cannot get out, we don't have point sets, but it means so on n minus 1, the functions are 0. So I can write it like this. It makes it easier to understand what are the quotients. So the quotients are the interesting part. So that will be C0, X, and Q. And then we take out.
It's just intuition, like this notation.
Yeah, it's intuition, but it works. So in philosophical, it works because it's the functions should be 0. It's a kernel. Yeah, it goes to x, q, n minus 1, and then on x, q, minus 1 should be 0. So we get functions which are 0. So the intuition, it works very, very well. We will see. So K would be C0 x cube n x cube, what we take out, 1, 2, so 0, take 1 out, it should be n minus k plus 1. So these are the complicated decipherers, but now we look at the quotients. So maybe, so let's look at A. K quotient A K minus 1. So we take our intuition. X cube n means we take out k. So I'm hoping x cube n minus k minus 1 quotient is 0 x cube n, we take out x, so n minus 1 is a plus, n minus k. U. So here anything which has dimension n minus k is gone. But we quotient out, or look at this quotient. So if you take this quotient, anything higher than n minus k still is in the quotient. But then we quote, okay, no, here, how can we see it?
Draw it. And draw it like some discs.
This, well, okay. Things which have dimension n minus k do not exist, and then we take a dimension higher and throw all out. So, but I know the result.
Double subtraction.
These are just this will be the disk, the open disk. And that's what makes it so interesting. So n, so the dimension of the disks is cis arcan n minus k, C0. So let's look at and this again. Now it's our balls. Which dimension? We keep dimension higher than n minus k. But everything, yeah, this is the way to see it. So here we keep everything which has dimension n minus k, then we get one higher and throw all out. So it's the only thing which survives after this. This is the important part. Okay. Now, half an hour for spectral sequences. These filtration lead to an exact couple, which relates to our signal exact sequence. So I'd like to jump right in how to construct a spectral sequence.
So I'm sorry, how do you see this equality?
There are some, we have to go back.
Union of cells whose boundaries.
The boundaries are gone.
Yeah.
The boundaries are already gone. This is a space where everything is gone, which has dimension n minus k plus 1. So only sets which live in something which has dimension n minus k exist. And then I take all the boundaries out.
Okay, can I draw something?
Yeah,
So here, these are all surjections, right?
yeah,
These rows.
yeah,
So it means that these x's sit in one another, right?
yeah,
Okay, so I suppose that this is correct to think that say this is my xn. I know these spaces are quantum.
I could see my two dimensionals you could have.
Yeah, let's do it like this. So this is my xn, okay? Then I have something with a lower index,
Yeah,
xn minus k, so it's here, right? So this is a
Yeah.
subspace.
yeah,
xn minus k. But I also have x with even lower index, xn minus k minus 1.
yeah,
Let me not write these numbers, but you know what I mean. xn minus k, xn minus k minus 1.
yeah,
And of course, I mean with the interiors. So now when I see something like this, right, I imagine that you have all continuous functions
yeah,
vanishing,
yeah,
vanishing at this circle, right?
yeah,
And inside,
yeah,
okay? And now you're dividing by this ideal when you take xn minus x minus k. So that's the part which you are deleting, right?
delete,
Yeah.
exactly.
So the only thing which remains is this ring here,
Yeah, it's open.
which is open. Yes.
That's all fine.
Yeah.
We can,
But how do I see that vis-a-vis balls?
well, that's.
It's from the symmetric fraction.
Because we pick the boundaries of the balls live in this, in a skeleton of dimension.
It is from this construction,
Yeah.
deductive construction by Kohlberg's, the CW. Okay.
The boundary of the balls live exactly in this skeleton.
Yeah.
That is done.
Okay.
Now, so this boundary survives and things higher dimensional. But higher dimensional will go as well.
Okay. Yeah. Thanks.
And how many copies does appear in the sum?
Yeah, this sum confuses me.
This n, which is the j equals to 1 to this lowercase n. How
I don't see any J on the right hand side.
No, these are all the same. It's the number of balls that I have glued.
What is J? Just is asking.
J is it runs up to the number of balls we have been gluing.
But in your previous, in your previous,
Did I forget my sums?
where do you have it? Here. Okay. That's okay. Thank you, Elmar. Yeah, we just don't remember everything. You're right.
So, okay, the time is getting even
Oh, yeah.
less. So
Now.
as a way to construct a spectral sequence. And it's what really makes it very attractive
Mhm.
is that the first page has only this case theory of these boards.
Which is rather.
So that goes, so the standard way is to consider an exact couple, it's called.
Exact couple.
Yeah. Couple, I think they call it.
Okay.
And so how does it work? We start, let's take, so K series is a half exact functor, and then we can extend to a long exact sequence, and we know what periodicity, but let's not care too much about it. We have something in the long exact sequence. So we start with a K minus 1. So then our inclusion map induces the map on K theory. So this is part of our favorite exact sequence. So then you go to the board. So in our boundary map goes back, but here, since it's homology let me take -1. This I will write a bit, it should be really seen.
Why did you say homology?
K theory is a homology theory.
Oh,
There's
yeah,
a spectral sequence in homology as well. So I take here -1. We know what velocity. And this is the boundary map. In K theory, and then we have alpha, okay, let me take another color, and then we go again. So that goes again to K, now it's 1 less 1 AK. So we can go with the quotient man. I didn't. Oh, yeah, I didn't. Well, we go something less. This one's AK. And then actually, by pot velocity, we go back here. But usually we should think that it goes -2 on and on and on and on. From this we can get a spectral sequence by taking, well, this is exact, going to D, this is exact. But if we define T1, okay, we do. So if we define T1, so we skip this inclusion. We take the boundary map and then project down. Rho times delta. So where does it go? It goes from K star 8K -1. So rho goes to K -1, we skip the inclusion and we project down. So this inclusion is skipped, so we project, if we would inclusion, the exact would be 0. But that goes now to K star 1 less. K -1, K -2. And these are these open balls. So that is here we have something like very nice groups. Z and K goes to Z and K -1. So our first page, you know, well, who knows the spectral sequences? Our first page is now a. Well, that's our first page actually, and then we define E2. So the indices we will okay. The indices I can make it. Anyway, so indices. So let's take it K. It goes A K Q. We define as image E1. So let me, so the value on which place here, which place we mean, this will be so we consider this as the space where we had this K -1 AK. No, it's a, right?
It should be upside down.
It's wrong. That has to be K. Yeah, that's wrong.
AK -1.
Yeah. This one. here as well. But that's the reason I don't like agriculture. First, we define as
Yeah, but
homology, so kernel P1, image P1. So this is our second page. So our first page actually sees K codes with P1 explicitly killed.
Q is, well, it's not a Q.
Q, P, O, X, L, you're right, that's a another confusion. So K, N, L, M, let me see. 26. So this is the way how one can get speculative. There's another. I would like to explain it a bit more explicit with all my with the text steps even.
you have first delta, I mean, the triple D partial and then row.
Yeah.
When I look at the diagram, it looks to me the other way around. First row, then delta. Show me this. Where is this is delta.
We skip this I and then we go down.
They go by this.
We go from here, we go row and then we go down. We go row down.
No, first you have to go by partial, by this.
Yeah. Partial.
Yes, then you skip this.
I found, yeah. Yes, the mistake is here. I found a mistake. Maybe that's a problem. Because we go one down.
Yes. Yeah, because you know, it's not clear which row you take, okay? And now it's okay.
Yeah, sorry. Yeah, from here we go row. We go up, row.
And it should be, wait a second. Okay. Yes.
So I then from this we get a derived couple. Now we replace it. And actually, and then
No, sorry, wait. I mean, why is it AK minus 1 by AK, not AK by AK minus 1?
It's the same type of thing.
The same type as you had before.
where yeah. Okay.
Maybe you could add indices, subgroups to these rows and deltas.
Yeah, thank you so much. Now I understand.
Okay, then, well, now from here we replace this by homology. And then on the, we work on, so let me make it here to save some time. So what we replace now is here we replace it with the one that comes from that's so which comes from one lower. So our K, you have K star, we replace by the image. Then we go here with the I star to twice. K star A K. And from here we go to our with the quotient map. We work on representatives to our E to well K M A K minus 1. And then up again. So from the exact couple, we can derive another exact couple, and then we go on. It's by induction. We work on here. We work on representatives, and then we have to show that it is really our red areas become an exact sequence, and then again we skip cis I and have the second differential. So that looks very
Colorful.
constructive, but it's not for computation. D1, we know perfectly. D1, we need some representatives, so there exists one in this image. That makes it difficult. So I would like to, in a way which I found better to see what exactly computes this exact spectral sequence. So if I will write it, not make exact trouble differently. So as a rectangular, so you see what really is happening. So our zigzag sequence, let's start with some, we started with some K1, A, K minus 1. So we had this inclusion to K1, AK. From there, we go to the quotient. K1. So K over AK minus 1. Boundary map to K0. A K minus 1. Inclusion. The induced morphism. K0. A K quotient O star K0 A K over A K minus 1 boundary map K0 A K minus 1. So this is our zigzag sequence. From here we could. Is it? No. Yeah, it's a mistake. One. Now we have. Yeah, our zigzag sequence. We could go back, but we look at long exact sequence in homology. So this is a scheme we can complete to a rectangular. So here, let's take another color. So this is exact. Now here we can go on with I star, A1, 1 higher, A plus 1. Quotient to K1, K plus 1, K. So boundary map K works, and here we can continue as well. So here we are, we go, it takes a quotient. K minus 1, and this would be K minus 2. Boundary map, it goes, actually, yeah, we could call it minus 1, but it's okay, K1. It's for some notation, it's better take minus. So we have A K minus 2, and here is inclusion. Now, the flag path, this one is exact. And our first differential, okay, A, E, 1 So did I have Kn? So let me, I tried the ideals to remember where I am, on which position. So then we said our K plus N of AK minus 1. This is our E1 page. These portions, it only cares about these portions. And this portion has a K theory of this. All groups, K groups are zeta number of disks, and some are 0. So some zeta 0, zeta 0. Our first differential D1. So here we see it, the black arrows are exact, but if I go that way, this is not exact. This is D1. And if I continue on D1, I have rho star rho, D square is 0. So that would be in the next D1. And we see we get really D1 square is 0. So we can compute homology. So here is D1 goes between our very easy groups and so on. Now, in the second page, that goes by induction. Okay, maybe I would like to change the color. So A2 Kn. So this one is minor taking one kind in the books. It's just I would like to remember on which position it is. Minus 1. This becomes homology. So kernel 1 image E1. So the second index M is the height. So this is our M. So this one goes from minus infinity to plus infinity.
That's a long way.
Excuse me?
It's a long way.
Yeah, but happily, this is a short way. In our finite, so the point is, this is not good. They have infinite elements, but this is stripped. And then our pages after n steps converge because our arrows go to 0. So, but to see this now, what is a D2? Here, D1, let's look here. So, okay, D1 goes up. Suppose we have an element in A2 is something here, which is an element here, such that it goes to 0. Yeah, okay. Maybe let me see if that is a good place to start. Maybe so it's 0. Yeah, no. Okay, if I go from here to 0. Ah, yeah, let's take here an element. Here's take an element. So an element in the E2 page goes here to 0. It lands here in 0. Oh. So what, since it's 0, so this is a composition of two maps. The last one has to be 0. So it's in the 0, this element, which is in the kernel. So we must have rho star, so the quotient map on dx is 0. So my delta x lies here. Here we have our delta x. But since it's in the kernel of rho star, and this is an exact sequence, so this comes from 1 up. So there's here we get an y such that y star becomes our delta x. Now what's the D2 differential does, it takes this y and sends it to rho star y. So our T1, T2 goes now that way. This is our T2. It goes 2 to the right and 1 up. Now, if we continue, now we replace again 2 by the homology, and then you see the T2 goes up, up, up. So in our notation, we have.
How you are defining E3?
Excuse me?
How you are defining E3?
In D3, I would have to take the same thing. So would I have to replace this? Well, this is a bit notation.
How higher differential come from?
Now the E2 is actually, it's not A. Here I have to take homology. No? I have to, in each place I have to take here kernel D1 image D1 in each of these places. Then I have my D2 is defined. And the problem is actually here. There exists a Y. That's my problem. So I know it exists, but I cannot. I don't not know yet if I can construct it. And then I go, okay, so let's have a look. So my
You are constructing the complex on the level of E2
yeah,
with new differentials.
yeah.
And so on. So
And I would like to show define some parameterization so that it goes, my D1 goes 1 to the right, D2 goes 2, 1 up. So yeah, so to see it, K. So T1, wait. One goes E, K, N, 1. So the K becomes 1 less. How does it go? K 1 less. So K is 1 less. So it's to E1 K minus 1 M. And P2 goes from
1, E1.
1. Yeah. 2 Km. Now it goes 1 up, but it moves to, in this case, to the left.
For every spectral sequence.
Yeah, that's so. Let's write it in. Let's write in say E1H. So see E1.
So I kind of lost track. The point of all of this is to compute the K theory of your CW complex.
We don't get the K theory, we get the groups of the graded object. So that we have a filtration. Now, if you have a filtration, you can take quotients and you get a graded algebra with your quotient out. Now, what these vector sequences really compute is the groups of the graded algebra. And then we have to reconstruct, we can reconstruct our K theory if we can solve this extension problem. And if you have torsion, we can't. there are two problems. The first problem is since we have only the groups of the created object, it's whenever there's torsion, it's not usually not possible to extract information of the groups which we want to have.
Is the case of non-orientable surfaces.
For example,
Uh-huh.
yeah, and that's interesting that you can, if it's in a classical case, you can write down here's a proof exact sequence, and you can write down the exact sequence. And so look where is look the infinity pages look pretty much the same, but then you have extension between Z2 over Z2 between Z2. So how do you extend it? And in one case, it's a direct sum, and in one case, it's Z4. It's strange. So our E1, that's something which we really see. That's pretty easy. So we have our M. And then we start with K0 of the number of points. See? So this is just the number of points we use. Then we have K1 of open intervals. And 1. So K0 of disk, open disks. That's M1. So that would be an M1, so that's N2, K1. So these are, yeah, this is okay, but here I should start with this bolts. That's why I prefer the disks. So K1 plus K from 1 to N3, and here we have 3 open 3 bolts. We can put the Qs. That is no difference. Yeah, and then it's also that's D1, 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 D1. Now, up the next place, we add 1 to the K theory that becomes K0 of an interval 0. 0, this is very convenient. 0, and then it repeats by pot periodicity. K1 plus.
Okay, so what's the eventually what do we have so far? It's out of.
Well, that would be 3-dimensional. You can continue with the dimensions. So it stops. The thing is that I don't know if it depends on the parity. It stops with some K, our highest dimension, J equal 1, N, E0, our Pn bolts. And then it stops. And here it repeats. U bolts. A0 sum of sigma. Two. A1 of the intervals.
So what's the proposition or theorems of?
So that's the J equal 1 and 0.
Elmar, you know, but you have 1 minute.
Yeah, 1 minute.
Okay.
So the proposition is that, well, so you go higher and higher, but once you are it is a D, this would be the Dn plus 1 would be 0. Then it stops. So that means in the language of spectral sequences, it converges. So we have our, so E infinity Km would be our En. Km. So what information do we get? So from cis diagonal, cis sum of groups. Cis is a K theory of the created object. So that is K zero of, you have a filtration of the created object. Okay. And here, K1, we take cis diagonal over the K1s up to the end. So you need to do it on this is on the last page.
But
That's
we want the graded associated object to K0.
Now what? Let's try it for K1. So
Not K0 of the
No.
graded object.
it's
Graded associated object to K0.
Yeah,
it's a graded
for me, it's very confusing.
associated object. Associated object to P1. Yeah, we have this book which we have to graded means we have some filtration, we get some groups. And again, but this is not what our spectral sequencer to get our spectral sequencer does the quotients. And that's the problem. That's why we have this extension problem. So yeah, we get Gn minus 1 plus Gn minus 1, Gn minus 2 plus and then G squared. So reconstruct our group, but if there's no torsion, you just count the numbers of sets. These are plain modules, you see that appears again, so you just count the numbers. If there's torsion, you don't know how to reconstruct the number. So that is what is a result, general result. In the case of my surfaces, everything stops here. And then D1 is enough. And if you would have time, you just write down the zeta copies, the D1, it's a boundary map, and in one go, you can get the K theory.
So you know the K theory for the surfaces?
No. Yeah, that's easy. Well, that's easy to compute with a six sequence. The difference is here, you can do it in one go.
Oh.
Yeah, we write D1, it's one differential, then we know it's infinity, and then we look at diagonal. So here we are lucky that this will always be a set, and we have no extension problem.
Which parameter to indicate we are considering surfaces?
No, that's when we stop. This is my blue line says we have two-dimensional CW complexes, and then our spectral sequence stops exactly here.
Exactly.
So D2 goes into 0.
So
It's a nil.
at the beginning, you are computing something K of C of Xn of some capital N. I don't know.
No. Xn, this was this boundary object.
Here?
No.
Earlier.
Very first, like before you introduce the spectral sequence. Here, okay, so which part on surfaces if
We start here. We constructed step by step
So it's
a CW complex.
This is called N skeleton.
Okay,
You just look at the superscript.
if I take N equals 2, then it's surface.
Yeah.
Yes.
Yeah.
Well, it's
That was my question.
Exactly.
The length of filtration.
The dimension.
C X 2 Q.
So what is the K-theory for the compact quantum surfaces?
It's the same as in the classical case.
Same.
Okay.
Graded. Because,
No, what do you mean with graded? With spectral sequence or?
no. Question was about K-theory of these quantum surfaces.
Yeah,
You
but
can
it
go
doesn't,
from the graded option.
yeah, but it doesn't compute it from this one. He just said that it's very easy to compute it from
Ah,
exact sequence.
without this.
Yeah, without this.
Well, we can check, wow, where's my?
But do you get torsion already in the surface?
Yeah.
Oh, yes.
Yeah.
RP2 has torsion.
For the non-orientable.
Yeah. Each time, do you remember this A and B1? Well, these are the map twice. So the boundary map, you have one unitary, one circle, one unitary, but it winds twice around the circle, and this is a factor twice. And then we get, the image is 2 zeta in the compacts, and then you have to portion out. And you keep here, well, I mean, we could do it for the quantum surfaces if
Time is up.
but time is up, yeah. Yeah, we have 1 point. We have the numbers of circles here, and then in the case, in the orientable case, this one is 0 to map. Yes. Yeah, that was no winding number. So this 0, this survives, that's K1, the number of cycles. In the other case, you have at least one group gets multiplied by 2 and sums up here. And that makes it, so you get here, to get it, so homology, you get a quotient. So this Z2, get here Z2, Z. And here it kills one of the, because it's the image, it's Z, so it kills one of the copies. It works perfectly in the case of 2 dimension.
But it also gives hope for higher dimensions.
Yeah. As I say, the problem is always find a formula for the higher differentials. In the classical case, it's the Steenrod operations, and it's already not very nice or simple. And in the case theory, we have the problem when where's my? Did I pass? Yeah, definitely. Yeah, that was, yeah. This element goes down. So here we have an existence problem. So we know it's in the kernel. We know it's 0, then this y from somewhere above exists. And this existence, it doesn't tell me how to construct the y, which y I choose. Now, I always the idea I can construct it by some extension, but
You are
here we
saying,
failed.
you are saying that you will have problems to get a E3 page.
Yeah, it's always, it's quite common. This is a common problem with spectral sequences to get to the higher differentials.
You stated theorem that says we can stop at some EN.
It stops, it will stop because we have a strip. So this goes a strip from minus infinity to plus infinity. But since it's a strip and the differential goes wide, always goes one step first to the left. And then they go to 0.
Construction have not yet finished it, so we know how to define the E2 page, but are still work in progress to get E3 something.
Well, we know that things exist.
The process is the same.
Yeah, we know that it exists. So we have this exact couple, we take the derived couple, then we take the derived couple from the derived couple. So that was, I showed you from, very briefly explained to get from the exact couple, a derived couple. And then you go on, the next derived couple. These are all abelian groups. We are talking about abelian groups. So what I did once with this triangle, final construction, and then I replace it. I have to show that it's well defined, that it's an exact sequence going in this triangle, but then we skip always this injection. And it's these, you see, it's really, if you look in the classical case, it's the boundary map. you ask, so you have something, you look at you clue a disk, and then you look for which K class do I clue my boundary graph. Works very well.
So, okay, could you go back to the previous page? Yes, so now we have the sequence over there, right? So it's a sequence of algebras, which we know some K theory at the beginning, right? So that's the.
No, that's the problem. That's the problem because in the spectral sequence, I construct it by deduction. But if I write down the spectral sequence, I have these ideals, and they are all live in the highest constructed ZW complex. That's a problem. That makes this induction step complicated. See, I have to lift my operators to the whole, to the ideal, which is to the whole algebra. I cannot stop. But then I project down, so there is a way to stop. So it's enough to we lift it once and project down. D1 works very well. Now, D2 is trivial, goes to 0. D3 tells me there is some element which I can map from a skeleton.
Oh, my question is, so we start with some sequence like that.
You will start with
This is we know, right? The question is, can we compute the K theory or not, right? So that's the. So all these efforts of spectral sequence is about to compute some.
Yeah, you get not the K theory, you get associated graded object. You're maybe lucky, and in lucky cases you can compute it. For example, for example, if you take the complex projective spaces, I say I would like to have the cluing map should land in the same generators. So for the complex projective spaces, you get something like Z, 0, Z, 0, Z, and then it goes on. And then you have zeros. And then Z again. Now, if you look at the differential, we go 1R, so K times R, and K minus 1. No, K times to the left, K minus times R. So you always hit 0. So this is already the infinity range. And then you see, okay, my K0, 0, and my K1, K0, so K1 is 0, K1 just counts sets. So you have exactly CBN has the K0 Zn. And K00, you can read it from the first page. So there are cases which you are just lucky, and then in one core you get the K theory. And then it's marvelous. There's some tool like vector sequences.
Okay, thank you so much. This was very fascinating. We are very happy.
Oh, thank you.
Recording.
Is this a, let me go, wait.